Question of why triangles, squares, and hexagons are the only regular polygons that tessellate. To give the explanation, I'm going to be talking about angles in terms of something called a turn. So a turn is the same thing as 360 degrees, or you might have seen 2 pi radians before. It's basically I find a much more intuitive way of thinking about angles is you just think of a turn as being one revolution. So with that out of the way, let's have a look at the interior angles of the various regular polygons, starting off with the one with the fewest number of sides, so 3, so a triangle, and going on to 4, which is a square, and 5, which is a regular pentagon, and we get to 6, which is a hexagon, and then we have our heptagon, and our octagon, and our nonagon, our etc., 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 getting all the way to a circle, which you kind of think of as an infinite-sided regular polygon. So, for our triangle, we have interior angles of 1/3 of a turn. For our square, it's 1/4 of a turn. For our pentagon, it's 3/10 of a turn. For our, hang on, I made this mistake when I was recording last time. It's 1/6 of a turn for the triangle, 1/4 of a turn for the square, 3/10 of a turn for the pentagon, and it's 1/3 of a turn for the hexagon. And then eventually, if we were to zoom in all the way, we would see that the situation as we got closer and closer in to the circle would increasingly resemble just a straight line, which would be, you could think of it as being half a turn. Worrying about the specifics of the circle, I think, isn't that important for answering the question of why only this, and this work. And to be honest, I'm not mathematically fluent enough to be able to properly give you the reasons for why you would probably see the sort of pattern that's emerging where we have 1 over a number, 1 over a number, 1 over a number. These are the ones that work, and then for whatever reason it breaks when it comes to this. However, we can see very clearly that these circles are not going to tessellate. There's going to be big gaps in between them. Yeah, but anyway. So, as I've kind of gone into already, you can see here that with the case of the 3-sided, the 4-sided, and the 6-sided polygons, so our equilateral triangles, our squares, and our regular hexagons, we have a situation where we have a fraction that's 1 over something, or we think of it as well as being like any variant of these types of fractions that simplify down to 1 over something. And we can also see that as we go up the number of sides, the number that the 1 is over is decreasing from 6 to 4 to 3. And then it needs to keep decreasing, but the only things it could decrease to next would be 1 over 2 or 1 over 1. So 1 over 1, I think, would just make absolutely no sense as an object, and 1 over 2 we know is a circle. So, why do these types of shapes with these types of internal angles work, whereas these types don't? Well, if we were to think about it, what would happen if you put 3/10 of a turn next to another 3/10 of a turn, which we could think of as being where this next pentagon would logically click in. And then tried to keep filling this with pentagons until these all nicely clicked into each other. Well, the problem is that you'd end up with, if you did this, if you put 3 together, you'd end up with 9/10 of a turn, which is not enough to fully cover this gap. But if you try and stuff in another pentagon, the problem is that you end up crossing over. So if you want to add another 3/10 of a turn there by adding another pentagon, you end up with 12/10. But with these cases where you have 1 over some number as your fraction of a turn, and you just need to keep adding until you have that number that's on the bottom of these. So if you have something like a 6, you can just multiply it 6 times, and you get yourself a nice set of tessellating polygons, in this case triangles. Or if you wanted to do it squares, because each of these interior angles is a nice neat quarter of a turn, you just need to put 4 together. So a quarter plus a quarter plus a quarter plus a quarter equals 4 over 4 equals 1. So 1 complete turn. So that means that you're not going too far, and you're not getting the problem of not going far enough. And then with hexagons, we can see a similar idea take shape. We want to just put 3 together, because each of these interior angles is a third of a turn. And the problem is that there's no whole number in between 3 and 2. So we can't really do 1 over 2.5, because then we would need 2.5 of these to make a whole turn. Whatever, hypothetical shape we would have. Basically, we can't use any number that's in between 3 and 2 as the denominator of our turn, where our numerator is 1. So because there's no such number here, there are also no such regular polygons in between 6 sides and infinite sides, where you can click all of the interior angles together nicely at a point, and therefore there are no regular polygons that will tessellate in between 6 and infinity, and we rule out the case of 5 already, and we rule out the case of circles, so all we're left with is 3, 4, and 6-sided regular polygons. All we're left with are triangles, squares, and regular hexagons.